Hello everybody, this is the next video in a series of videos on Python programming for engineers. My name is Mark Bakker and I work at the Delft University of Technology. Today I will show how to use Newton's method to find the zero of a function, and I'll talk about a few things that some of you might have done wrong last week. After that, I'll show how to solve a system of linear equations. First, let's start by writing a function. And I'll write a function for f of x is equal to 1/2 minus e to the power minus x. We'll go to Canopy and we'll type def f of x. So the name of the function is f, and we create a return variable rv is equal to 0.5 minus x of minus x. Hit enter one more time, and I've defined this function. But I've done something wrong, as you will see in a second. When I type f of, for example, 3, I don't get anything back. If I type a is equal to f of 3 and I say print a, I'll get none. Why do I get none? Because I forgot to return the return value. So what I should have written is, using the up arrow to get the function back, I should have ended the function by saying return rv. Because now it will return the value of the return variable at the end of the function. If I now call f of 3, it does indeed return the correct value. Notice though that there now is not a variable called rv. If I type rv, it says name rv is not defined. Rv is only defined within the function, and return rv doesn't mean it returns the variable rv. It means it returns whatever value is stored in rv. And I can call it anything I want. I can type a is f of 3. Now a has that value, and there is no variable named rv. Rv is only defined within the function. Well, I hope that clarifies a few things. Let's now try to do Newton's method. And for that we scroll back down to see what Newton's method was all about. Newton's method is an iterative method where if you start at a location xn, the next best guess for the zero of our function is equal to xn minus the function evaluated at xn divided by the derivative of the function evaluated at xn. Let's try to write that. So we create a new Python function. We might as well use this plus sign here. This creates a function right for us. Remember, when you save these functions, you have to give it the extension .py. So we say file save, and let's call this Newton.py. The first thing we do in a function or in a Python file is we import the packages we need. We need Pylab. From Pylab import star. Then we start writing our Newton's method. Newton's method took 5 arguments. The first one is the function. The second one is the derivative of the function. That's called func p for func prime, right? F prime is the derivative of f. A starting value for our search, and 2 keyword arguments, a tolerance. Let's call it 1e minus 6, and that variable is called tol. And then there is a keyword argument n max is the maximum number of iterations. Let's call that 10. Then I enter a colon, I hit enter, and now I'm inside the Newton's function. First of all, we have to evaluate the function at the starting value at xs. Then we go inside a loop. We're going to loop n max times, that's the maximum number of iterations, and we break out of the loop when we have reached the tolerance. For I in range n max, what do? I calculate the derivative of the function by calling the function func p, which we have passed to Newton, to the Newton method, and I calculate the new value of the new best value of my zero, which is xs is equal to xs minus f divided by fp. Remember, f was calculated here, fp was calculated here. Once this is our new xs, let's calculate the new f. F is equal to func at xs, and let's see if we make any progress. So I say print xs and func of xs to the screen. So I know whether I'm making good progress or not. The next thing I do is, inside this loop, is I check whether I reach the tolerance. If the absolute value of f is smaller than the tolerance, I break out of the loop. If I've not reached that tolerance, I don't break out of the loop and I do the next iteration. So this is the end of the loop. If I break out of this loop, or if I reach n max, I go to this line, and this line is if the absolute value of f is larger than tol, then what has happened, that means that I've done this loop n max times, but I haven't reached the desired tolerance. So that means I have reached the maximum number of iterations without finding the zero with enough accuracy. So I say print max number of iterations reached. Well, maybe I should say error, right? Because that's not what we want to have happen. So that error is printed, or that warning is printed. And then at the end, the last thing I want to do is I want to return XS. That's the zero I found. Or if I printed this error, then that's the best value I found so far, but it has not converged yet to within the tolerance. All right, so we'll save this file. I go to my Python prompt. I type run Newton. And I cannot find it. Why can I not find it? Because I'm not in the right working directory. So I click on this little arrow up here. I say changed to the editor directory. So I'm now in the directory where Newton is. And I do again run Newton. And indeed, now there is a function Newton. If I open the parentheses, you see exactly the function arguments and keyword arguments that I specified there. What are we going to call this function with? Well, let's do it for the sine function. All right, I said, well, let's try to find the zero of the sine function starting at x is equal to 1. For that we need the function, which is sine, and we need the derivative of the function. And the derivative of the sine function is the cosine function. Now, some of you wrote new functions for sine of x and cosine of x, but there's really no reason for that, because sine of x or cosine and cosine of x already exist. So we can simply call Newton. The function is the sine function. The derivative of the sine function is the cosine function. And our starting location is 1. Let's leave the tolerance and the nmax as they are, the default values. We hit enter, and you see what it does. We started searching for the zero at 1. The next best estimate was minus 0.55, then it was 0.06, then it was 9 times 10 to the power minus 5, and then it was 10 times 10 to the power minus 13. So in 1, 2, 3, 4 iterations, it finds 0 to within 10 to the power minus 13, which is pretty darn quick. The real zero of the function, of course, is 0. The sine of 0 is 0. But as I said, it depends very much on your starting location, because the sine of x is 0 every pi. So if we would have started at a different starting point, for example, if we would have started at 1.5, we would have gotten as answer within 1, 2, 3 iterations, we would have found a 0 that is 10 to the power minus 15 at minus 12.56. Or if we divide this by pi, we would figure out we find minus 4 pi. So if you have a function that has multiple zeros, you never know which one the Newton method will end up with. That's all I wanted to say about finding the zero of a function using Newton's method. Next, let's try to solve a system of linear equations. Imagine we have 3 equations in 3 unknowns, and the equations are written down here. A plus 2b plus c is equal to 1, 2a plus 4b plus 4c is equal to 2, and b plus c is equal to 3. To solve this system, we're going to write it as a matrix times a vector is equal to a vector of known values. In this case, the matrix is stored in a two-dimensional array. Let's call it A. A is equal to array two-dimensional array, so it has the first row, let's get rid of that statement, has 1 times A plus 2 times B plus 1 times C. So it's 1, 2, 1. The next row is equal to 2 times A plus 4 times B plus 4 times C. And the last row of the two-dimensional array is 0 times A plus 1 times B plus 1 times C is equal to 3. So if you now do print A, you see it is 1, 2, 1, 2, 4, 4, 0, 1, 1. That's correct. Now the right hand side is 1, 2, 3. That's the values we want to get at the end. So let's call that RHS for the right hand side. We make that into a one-dimensional array. Array 1, 2, 3. And right hand side is now 1, 2, 3. To now solve for A, B, and C, all we have to do is call the solve function. And the solve function is part of the linalg for linear algebra package, and that's a sub-package of NumPy and Pylab. So it's automatically imported when Pylab is imported, and we can type linalg.solve for linear algebra.solve. See, it tells us it needs a two-dimensional array A and a one-dimensional array B to solve a system. We've called our two-dimensional array capital A, and our right-hand side, or our B vector, we called RHS. We hit enter, and we get as a solution -5, 3, and 0. So A is -5, B is 3, and C is 0. We can store this, of course, this vector, by typing sol is equal to linalg.solve A, RHS. So now as the vector or the one-dimensional array sol has now the solution, and to verify whether this is correct, we would have to type, we have to have matrix A times vector sol. That is a matrix multiplication. So we cannot do A times sol. That doesn't give us the right answer. We have to do a matrix multiplication, and the matrix multiplication is called dot. If we open the parenthesis, it tells us it's the dot product of two arrays. And in this case, the two arrays are capital A times sol, right, which is this array, two-dimensional array A, and the solution is the values of A, B, and C we just calculated. And if that is correctly solved, we should get 1, 2, 3. And by golly, we do get 1, 2, 3. So it seemed like it worked correctly. That's all I got for you today. Hope to see you next time.